How many of you have been in a situation where you're working on an incident and you start to think the issue isn't actually in your system at all? Yeah, happens to me a lot. Reminds me of a situation a couple months ago when I came home from a camping trip, really excited to return to civilization. I turn on my hot water and there's no hot water. So the question is the problem somewhere in my apartment, in the faucet? Is the problem in the water heater? Is the problem that there's no gas in my building? From my position in my apartment, it's really hard to figure that out. And that kind of multi-phase upstream provider system is something that happens all the time in software, and specifically at render. At render, we've found that these cross-provider issues can be uniquely difficult. You don't have all the debugging tools you're used to, and there are also these social factors that come into working with support teams and organizations that you just don't have an existing working relationship with. So today I'm going to give you a bit of detail into what render is and why we care about this, and then I'm going to talk about various techniques and strategies we've learned in the course of working on these kinds of incidents. And I'm going to go through 3 different incidents to kind of illustrate those examples. All right, so what is render? Render is a platform as a service, which means we take our users' code, databases, applications, and we make sure that they are deployed and up and running and serving traffic on the internet. This means that at Render, we are both a platform provider, but we are also a platform customer. So we use our own upstream providers to have compute, storage, networking primitives. And a lot of times when we're debugging an issue, we're trying to figure out what part of that system is having the problem. So that takes me to my kind of core part of the talk today. I'm going to talk about 3 different incidents that all have roughly the same symptom, but all have very different outcomes. So the core symptom I'm going to be talking about is network problems. So our users' make a web request to their website, and then we have upstream providers doing our CDN and load balancing that send requests into our render cluster, in which we're running an HTTP proxy, which is in charge of, again, routing those services to the exact instances of user applications. So in my analogy, maybe the upstream provider is like the city gas, the proxy is my water heater, and then the user application is like my faucet. So the core symptom here is the end user is getting an error, or the end user is getting a very slow request. And then the question in each of these incidents is, but where? Where is it coming from? And yeah, we'll get into that now. So incident number 1, these are going to kind of go from relatively chill to increasingly complicated. So starting off fairly simple, we got a report from one of our highest traffic users that they were seeing an increase in errors. Normally, these kinds of customer reports are filtered through our support team and they do some initial triage. But in this case, the issue was escalated in a kind of unusual manner and it turned into an incident pretty fast. So we started digging into this error. It wasn't an error that was being explicitly returned by either our system or our user's application. So our thought was maybe this is something to do with our upstream provider. So we opened up a support ticket with them, asked if they were seeing anything, and unfortunately, no, they didn't know what was going on. Everything looked normal on their side. So we kind of went back to the drawing board and dug in more with our customer, kind of looked more at the characteristics of these requests, and eventually determined that their code, while it was not producing these errors, it was unexpectedly terminating WebSocket connections that led to this kind of ungraceful connection closure and failure that manifested as this unexpected failure at the end. So in this example, the issue was in my sink in the user application. Yeah, so this is pretty common, and we have a couple lessons that we've learned working on these kinds of incidents. The first is that these kinds of incidents actually tell us a lot about our product. Because we're a platform as a service, we want to build a tool where users can answer all the questions they need about their own system, troubleshoot their own issues, view logs, observability, etc., and solve their own problems. So when we have situations like this, it's a signal to us that maybe there are some gaps in observability or tools we need to improve to allow our users to figure out what's going on for themselves. This incident also taught us a lot about our processes and the importance of like that kind of sequence. Our support team is really, really good at helping users troubleshoot their common problems or configuration or application issues in their code. And the fact that this leapfrogged our support team and went straight to engineering incident response was actually kind of counterproductive in driving to quick resolution here. We on the engineering team are used to working on systemic platform-wide issues, and so we're biased to assume like that's what we're working on when we see an issue like this. So working on this as an engineer, it really emphasized like the support phase and triage process is like really critical to driving a good resolution to these incidents. All right, incident number 2. So in this incident, a different user reached out to us because they were starting to see some very, very slow requests. This is kind of a heat map of showing the impact and then eventual resolution of this issue, where a small percentage of requests were taking like multiple seconds to resolve. Because this was just a single user reaching out, we initially had this assumption that like, well, just one user seeing this problem, maybe it's something on their end. So the good news was that at this time we had also started investing in better tracing in our HTTP stack. We were able to add traces and see and capture some of these slow requests and see like where exactly were they spending all their time. And in this case, you can see the kind of teal bar there. This is well within our own code. It doesn't actually get sent to the user service till like 5 or 6 steps down below. And so this is telling us exactly like where all this time is being spent. And so this was just like critical. Before this point, we were like, well, it goes into our thing and it eventually comes out, but we don't really know like where it's spending its time. So once we had that, we were able to zoom in even further. We added a couple more spans and saw that the slow part was related to accessing the data that was used to route these requests to the right service, this metadata store effectively. And to access the metadata store, you had to take a lock. So our initial suspicion was, okay, some kind of lock contention is going on here. And then the next question is like, who is it contending with? Like, where's the competition? Because this was a read lock. So then we were able to zoom in even further, looking at specific slow requests on a specific pod at a specific time. And we used CPU profiling to see what was the code that was running at this exact time. And that was what allowed us to really solve the issue. And so we found that it was fighting with this process that's in charge of syncing in the background this metadata, keeping it fresh and reconciling updates. And so we had to make some changes to those locks to allow requests to never get blocked by this process. And it was a really interesting bug because it wasn't like we had made a code change that had caused this regression, but it was this kind of like creeping, very slowly building thing, because the bigger this map was getting, the longer it took to update, and just, frog boiling in water kind of feeling. All right, so yeah, this is the example where it's, inside the render controlled universe, which meant we could fix it ourselves, which is great. This would be the water heater in my analogy. So takeaways. An initial bias that kind of slowed us down in the beginning of this incident was the assumption that because only one user was reporting an issue, then that issue must be related to their configuration. It turns out that some users just have different needs or expectations. This particular user was a lot more latency sensitive than other customers that we had worked with. And so they were kind of the canary in the coal mine for this slowly worsening performance. And they helped us like catch it early, basically. So that was like a really useful thing to realize in this incident. The other big takeaways here were the kinds of observability that were most helpful for us. And really it was about specificity and boundaries. So we weren't sure, is the slowness in our stuff, in their stuff? The critical thing was to observe the boundary between our stuff and their stuff and see what exactly is happening at this boundary. and then getting really specific, like seeing these trends of slowness across our whole system was pretty unhelpful. But once we looked at a really specific pod at a specific time, we could see, oh yeah, this is what the CPU is doing right now, and give us a real smoking gun. All right, so it's all been building to this. Incident number 3. We started seeing these really weird traffic spikes or latency spikes. It was a combination of errors, actually the errors from the first incident, and then also very slow requests similar to the second incident. And these spikes, they were all under 10 minutes. They were all in Ohio, in US East 1, and they all were during, business hours, never on the weekends, just, during normal business hours, it would just suddenly get really slow. Yeah, so we see familiar themes of connections failing and slow requests. And fortunately, we had our tracing nicely in place, and this was able to show us that, in fact, yeah, the problem wasn't in our system. This blue bar shows this is the time from when this probe check started to when it actually reached our system, and it spent all the time somewhere out there in the ether, in the internet. All right, so with that evidence, we decided to reach out to our upstream provider and say, hey, what's going on? We're seeing these slow requests, we're seeing these errors. Can you help us? And they didn't see anything. They saw kind of, background radiation levels of errors. The internet is a tough place, stuff goes wrong. But they didn't see these spikes and couldn't really help us. They gave us some kind of general debugging around these connection handlings, but couldn't help us too much. So we were left in a kind of challenging situation where we couldn't see what was happening because it wasn't in our system, but our provider wasn't seeing anything. So we needed to rule some things out and do some more tests. So what we did is basically try to form different hypotheses and then reason about what would have to be true about the world if this hypothesis was true. So our first idea was maybe these proxies are somehow failing to initiate or accept incoming connections. They just can't actually start the connection in the first place. This would explain the behavior, but we couldn't really see any reason why this would be happening in Ohio specifically. We weren't getting more traffic in this region. These periods of slowness weren't correlated to traffic spikes on our platform or anything else we could see. So that didn't really explain the situation. Next, we were wondering about our cluster networking. So we use Kubernetes. We have inside the cluster networking that allows nodes to talk to other nodes. Maybe something was going wrong with the connection in the cluster itself. So we poked around at some observability for cluster networking as a whole and tried to see if we could find any evidence that these connections were failing anywhere outside the context of HTTP requests. And we couldn't find any evidence of that either. So our third theory was network throttling. So our underlying compute provider, their instances all have a certain bandwidth quota where if you exceed that bandwidth quota, they reserve the right to throttle you. So they're not always going to throttle you, but if they're particularly busy, they can cut you off, basically. And so this felt good, right? This explained why we saw these connections not completing. And it could also kind of have this noisy neighbor explanation where maybe this cloud provider saw a bunch of traffic at this time, and then they needed to throttle us. So this was a good explanation. We decided to perform an experiment. The experiment we crafted was basically to really crank up our instance sizes and make the bandwidth allowance really, really huge. So there's no plausible way we could get throttled. So we made this change, really big instances, and the same thing happened the next day. So at this point, we were getting pretty frustrated. Yeah, this feeling of I can't see it. What's happening? I've looked everywhere. We decided to go down a layer of abstraction and start looking at some packets. So we used TCP dump to capture packets on one of these instances, we were able to capture one of these episodes. And this is basically what we saw. We saw upstream reaching out, saying hi. Our proxy said hi back, and then nothing. And then we said, hey, you still there? Then nothing. And then we say, all right, I give up, goodbye. And then several seconds later, the upstream saying, oh, hi, here I am. And that packet significantly was a retransmit, indicating that that was, the second or third time it had sent that packet. So we were actually able to plot all the retransmitted packets in this period, and yeah, it like perfectly highlighted this 10-minute period of network issues. So we decided to go back to our upstream provider and say, hey, what's going on with these with these packets getting dropped? And with that information, with our kind of high-level trends about when is this happening and what are the symptoms, what have we ruled out, and then also this particular TCP handshake failure, they were able to say, yeah, that looks like network congestion, that looks like packet loss, and they were able to zoom in into their own observability and their own systems, and they found that indeed these were periods of very brief but very high congestion. Also, it was ultimately a noisy neighbor problem, similar to what we hypothesized earlier, but just kind of at a different layer. And they actually ended up provisioning more underlying compute and more underlying network capacity that resolved the issue. All right, so takeaways from this incident. There's some kind of interesting kind of social, emotional biases going on here. One was we had this feeling that like, surely we can't be the only one noticing this issue, right? It seemed really severe. If this is really a problem with the upstream provider, surely someone else would have reported it. If you notice, that's kind of the inverse bias I had in the last incident. It just turned out we were the ones who were really sensitive and really picky about our network performance. And so, yeah, we drove this to resolution and were able to solve this issue because we had that sensitivity. And then the other big takeaways here are kind of how we felt around in the dark in this system that we couldn't actually see inside of. We used process of elimination to rule out and kind of reduce the search space of where issues might be. And then we tried to focus on both trends and specifics when sharing back to our support team. Showing the high-level trends of when this is happening, et cetera, was not quite enough. And then we really needed to provide this like concrete evidence of this is the TCP handshake, where's the packet conversation to really break through. So wrapping up here, what makes these kinds of incidents hard? I think there are kind of two big things. You have your technical limitations. You're debugging a black box. You're debugging someone else's code you can't look at. You can't attach a debugger. You can't add log lines. There's just like a lot less you can do. You don't have your normal tool belt. And then you have these social challenges. You don't have a strong working relationship with the people you're collaborating with. And they're also just looking at a very different side of the system, right? They might not know about your application. They don't know what's going on in your systems. They can only see their side of the situation. But these are solvable problems. You can do it. Like you can figure out how to infer things about these systems with limited tools. You can use tracing, profiling, focus on boundaries, focus on specific behavior of what is happening between these two systems. And then you can invest in and prioritize building these social connections. It can be really frustrating to be on the other side of a customer support case. And like at Render, we are on both sides. Our users reach out to us when they're having trouble and we want them to have a good experience. And then we reach out to our upstream providers and have similar experiences. And in both cases, really just trying to build context and build empathy is what's critical, right? You can have a really strong theory, a really strong technical opinion about what's happening, but unless you can figure out how to communicate and build that shared understanding with your counterpart at your upstream provider or wherever, it's hard to make any progress. So these problems are solvable, and you can do it.